All right, let's get right into it. In this explainer, we are doing a serious academic level dive into the science of tsunamis. We're going to break down how these incredibly powerful waves are generated deep in the ocean, how they can cross entire basins at the speed of a jet, and what we can actually do to protect our coastlines.
It all starts right here. Far from any shore, completely silent, an unbelievable amount of energy gets transferred into the water. This is the final, terrifying moment of that energy's journey. But our story, our analysis, begins miles below the surface, where the whole thing is set in motion.
So, to make sure we cover all our bases, we've structured this into 5 key areas. First, we'll nail down the definitions. Then, we'll get into the physics of how these waves actually work. After that, we'll connect it to the real world, what causes them and what damage they do. Then, we'll look at how we spot them. And finally, what we can do to mitigate the risk.
Okay, first things first. Let's get our terminology straight. In any science, and especially for an exam-level review like this, having precise language is absolutely critical. So the word itself, tsunami, comes from Japanese, and it literally means harbor wave. And that name is just incredibly insightful. Think about it. Fishermen could be out in the deep ocean, and a tsunami wave might pass right under them, completely unnoticed. But then they'd return to port to find their harbor and their entire village just devastated. It perfectly captures this idea that a tsunami isn't one wave, it's a series of them, and its destructive power gets focused in coastal areas like harbors. And this leads us to a really important distinction: the tsunami earthquake. Now, this is a critical concept because it tells us something huge. Not all underwater earthquakes are created equal. Some are just way more efficient at generating a tsunami. These specific quakes manage to displace a massive volume of water, creating a wave that is way out of proportion to the quake's seismic energy. It's a specialist, and a devastatingly effective one. All right, so we've got our definitions down. Now let's get into the physics. To really understand the immense power of a tsunami, you have to understand the mechanics of the wave itself. These numbers right here are what make a tsunami a completely different beast from a regular wind-driven wave. A normal wave at the beach has a period of, a few seconds? A tsunami's period can be up to 90 minutes. Its wavelength, the distance from one crest to the next, can be 200 kilometers long. And here's the kicker. Its energy isn't just a surface phenomenon. It involves the entire column of water, from the seafloor all the way to the surface. That is where all that incredible power comes from. So, how fast does this thing move? Well, it all comes down to this really elegant formula. V is velocity, G is the acceleration due to gravity, that's a constant, and H is the depth of the water. The key thing to see here is that a tsunami's speed is basically controlled by one thing: the depth of the ocean. Deeper water means a faster wave. It's that simple. And here's what that formula looks like in the real world. In the deepest parts of the ocean, a tsunami can travel at 950 kilometers per hour. That's the speed of a commercial jetliner. Now here's a fun little paradox for you. Technically, scientists classify this as a shallow water wave. I know, that sounds crazy, right? But it's because the wavelength is so enormous, hundreds of kilometers, that even an ocean 7 kilometers deep is considered shallow in comparison. And it's that very property that allows it to travel so incredibly fast. Okay, so we've got the physics. Now we can start connecting those mechanics to the real world. What kind of event actually kicks one of these off? And what really happens when all that energy finally reaches land? For the biggest, most destructive tsunamis, the trigger is almost always a very specific type of earthquake. You need a few key ingredients. It has to be big. It has to be shallow. And it almost always happens in what's called a subduction zone. That's where one of Earth's tectonic plates is sliding underneath another one. This diagram shows you exactly how it works. In one of these subduction zone quakes, the top plate snaps upwards, violently shoving the seafloor up with it. It acts like a giant paddle, instantly lifting the entire column of water above it for hundreds of square kilometers. All that potential energy is then converted into kinetic energy as gravity pulls the water back down, sending those long, powerful waves racing outwards. And the consequences when those waves hit are just catastrophic. Drowning is, of course, the main cause of death, but the secondary impacts are just as deadly. You've got this wall of water filled with debris that acts like a wrecking ball, causing buildings to collapse. You get explosions from ruptured gas lines, electrocution from downed power lines. And the long-term effects? Contamination of fresh water and sewage systems can threaten a community's survival for months or even years after the wave is gone.
So given those stakes, you can see why early detection is everything. Let's look at the incredible technology we've developed to try and spot these waves while they're still far out in the open ocean. The absolute cornerstone of our modern warning system is a network of buoys called DART. That stands for Deep Ocean Assessment and Reporting of Tsunamis. And its entire job is to detect a tsunami when it's still just a few centimeters high, hundreds or thousands of miles from shore, giving people that critical, life-saving time to evacuate.
This diagram shows you the whole DART system, and it is a brilliant piece of engineering. It all starts with a pressure recorder sitting on the seafloor, miles down. When a tsunami passes over it, the sensor picks up that tiny change in pressure and sends a signal using sound waves up to a buoy floating on the surface. That buoy then transmits the data via radio up to a satellite, which beams it back down to tsunami warning centers on the ground, all in a matter of minutes.
So let's just walk through that again, step by step. The unit on the seabed is constantly measuring the weight, or pressure, of all the water above it. When a tsunami passes, even if it's only a few centimeters high out there, its huge volume adds extra weight, increasing the pressure. That change is the trigger. The seabed unit sends an acoustic signal to the surface buoy. The buoy radios a satellite, and the satellite alerts the warning centers. It's how they get real-time confirmation that a tsunami has actually been generated after an earthquake. Okay, so a tsunami is detected. Now what? Scientists need a way to quantify its power, and that's where something like Abe's magnitude scale comes in. You can think of it as being kind of like the Richter scale, but for tsunamis. It gives us a single number to classify the size of the event. The formula basically looks at the wave's maximum height and the distance it's traveled from the earthquake. And because it's a logarithmic scale, each whole number you go up represents a massive leap in energy, which helps scientists rapidly assess just how big the threat is.
And that brings us to our final section, mitigation. Knowing a tsunami is on the way is one thing, but surviving its arrival is another challenge entirely. So let's look at the strategies, both natural and man-made, that we use to protect coastal communities.
You know, our first and often our most effective line of defense actually comes from nature itself. Healthy coastal ecosystems like a dense mangrove forest or a wide, intact coral reef act as incredible natural barriers. All their complex structures create enormous friction, essentially combing the energy out of the wave, slowing the water down and reducing its height before it ever reaches people.
Now, where those natural defenses don't exist or aren't enough, we turn to heavy-duty engineering. Tsunami walls are exactly what they sound like, a strategy of brute force, a massive physical barrier designed to simply stop the wave in its tracks. Floodgates work on a similar principle, allowing us to seal off rivers and estuaries to stop the surge from pushing deep inland.
There's also another engineering approach that actually kind of mimics what the natural reefs do. Structures like these concrete tetrapods aren't meant to be an impenetrable wall. Instead, their whole job is to break up the wave's energy. Their complex, interlocking shapes force the water through a chaotic maze, which dissipates its power before it can slam into the shoreline with full force. And all of this brings us to our final and maybe most important question. We've seen the power of these massive engineered solutions, and we've seen the effectiveness of natural ecosystems. The real challenge for every coastal community on the planet is finding the right balance between the two. How do you build for safety while also preserving the natural buffers that not only offer protection, but so much more? That right there is the fundamental question at the heart of tsunami science and safety today.